Okay guys, this is section 7.1. In this section our goal here is to be able to graph and use exponential growth functions. So a little bit of vocabulary to start out. An exponential function is just a function of the form y equals a times b to the x power. Specifically, an exponential growth function is if the a is greater than 0 and b is greater than 0 in that function y equals a times b to the x, and it has a growth factor of b. So that growth factor is just some quantity b in the exponential growth function, y equals a times b to the x, with a is greater than 0 and b is greater than 1. So that distinctive trait right here, a is greater than 0 and b is greater than 1, makes the exponential function a growth one. Okay, and lastly, that an asymptote is just a line that a graph approaches more and more closely, but it's never going to touch it. Okay, so we're going to look at and see what asymptotes or kinds of asymptotes exponential growth functions can have. So these are what exponential growth functions look like. This is the parent graph or general shape. So the function f of x equals b to the x power, where b is greater than 1, so that makes it a growth function, is this parent function for the family of exponential growth functions with base b. The general shape of the graph is shown below here. Okay, so it makes sense that it's a growth function because it's rising from left to right and it's passing through the points 0, 1, and 1b. And also over here, it's going to be approaching closely the x-axis. So our x-axis is the asymptote. It's going to get really, really close to it, but it's never going to cross it. Okay, and lastly, the domain of f of x equals b to the x power is all real numbers. So from left to right, we're hitting all the negative and hitting all the positive, so all real numbers. And then the range is y is greater than 0. And notice that it doesn't say greater than or equal to 0 because we're not ever going to hit 0 on the y or cross the x-axis. So it can't be 0, it can be greater than 0. So again, the domain for exponential functions is always going to be all real numbers, but for the range, it can vary, okay? The range is just as y is greater than the number that your graph is approaching, or your asymptote. So let's graph one. For example here, we're going to graph y equals 2 to the x power. So we're going to put this in the graphing calculator, make a table of x values that we could plug into x and get a y value back. So let's go ahead and put that in the graphing calculator, y equals 2 to the x, and second graph it. And you might have to tab up or down a little bit in order to see some of the negatives, but from negative 2 to 2, or even 3, that's going to be sufficient. Okay, so let's do just negative 2 to 3. Okay. So negative 2, negative 1, 0, 1, 2, 3. So at negative 2, from your table is 0.25. At negative 1, it was 0.5. At 0, it was 1. At 1, it was 2. At 2, it was 4. And at 3, it was 8. And again, those are just gotten by taking all the x values, plugging it into x up here in the equation, and getting back the y value. Okay, so let's now graph this on our graph. So at negative 2, it's a quarter of the way up, so very, very close to the x-axis. At negative 1, it's a half of the block up, or unit up. At 0, it's 1. At 1, it's 2. At 2, it's 4. And at 3, it's 8. Okay. So now we're going to connect them with our smooth curve. So here we go. Okay. And if we notice, if we think about a domain that is all real numbers, so the fancy or you could do negative infinity to regular infinity, and it is growth because we're growing, rising from left to right. And the range, if we look up and down at our y values, well, it's never going to hit the x-axis. So our x-axis is the asymptote. So we're going to hit all the y's bigger than 0. Okay. Looking at our next one, we need to graph 1/2 times 4 to the x. So again, we're going to make a table of values by plugging this into y equals. So 1/2 times 4 with an exponent of x. Second, graph it. And here we go, from -2, and we'll just say to 2 again. Okay. So at -2, we'll say to 2. So -2 from our table is 0.03 rounded. -1 was 0.125. At 0 it was 1/2. At 1 it was 2. And at 2 it was 8. And it keeps growing in the y direction. So again, this is growth. And why it is growth? Because our b, or the number that has our exponent, is greater than 1, so it is growth. Okay, so if we go ahead and graph these, it should go up from left to right, like an exponential growth function should be. So at -2, it's really, really close to the x-axis. And at -1, it's even higher a little bit. And at 0, it's 1/2 of a unit up. At 1, it's 2. And at 2, it's 8. So it's growing really, really fast. And if we connect them with our smooth curve, it's going to keep growing really, really fast. So here we go. Again, if we look at domain and range, the x values, again, we're hitting all of them, the negatives and the positives. So you could put either or. And then the range, well, our asymptote is still going to be the x-axis. So we can't have y being 0. We can have everything greater than 0, though. Okay? And our next one here, -5/2 to the x power. Again, let's put that in the calculator. So clear that one out. Negative, parenthesis, alpha y equals it, 5/2. And raise it to the x power. And again, from -2 to 2 is fine. So let's see how this one turns out. So -2 all the way to regular 2. So here's our table of values coming from the calculator. And let's go ahead and graph these. So at -2, it's negative this time, 0.16. At -1, it's almost 1/2 of a unit. At 0, it's -1. At 1, it's -2.5. And at 2, it's -6.5. Okay. Then, if we graph it with our smooth curve, okay, this one's reflected. But it's still growth because if we had it reflected, normally it would be looking like this. So it's still growth. But why it's upside down like that is because of this negative sign to begin with, and it flipped it over the x-axis. Okay, so if we look here in our domain, we're still hitting all the real numbers from left to right. But the range in this case, we're still never going to hit 0 because that's our asymptote. It's always going to approach it but never touch it or cross it. So it's going to be y, and in this case I don't have any positive y's, I have all the negative ones, so this one's less than 0. Okay. Translation, so we can actually translate or move around these exponential functions on the graph or on the coordinate grid. So to graph a function of the form y equals a times b with an exponent of x minus h plus k. Okay, we're going to first sketch the graph of the normal exponential equation y equals a times b to the x, and then translate the graph horizontally by h units and vertically by k units. We've done this all before, okay? We did this when we graphed absolute value functions, or the v's, okay? So moving it horizontally h units and vertically k units. So let's do that in example 4. Okay, so when we graph this one, we're still going to use just the table. So go ahead and put this one in the y equals. So 4 times 2 raised to the x minus 1, but make sure to tab to the right to get out of the exponent, and then minus 3, second table. And again, negative 2 to 2 is fine. It kind of gives us a rough shape of what we're looking at here. That's growth. So what we could do here is make our xy table and copy it from our graphing calculator. So if we put in these 5 x values into the normal original equation, okay, at negative 2 we get back negative 2.5. At negative 1 we get back negative 2. At 0 we get back negative 1. At 1 we get back 1, and at 2 we get back 5. So let's graph that. At negative 2 we can go down 2.5, okay, and at negative 1 it's negative 2. At 0 it's negative 1. At 1 it's 1. At 2 it's 5. Okay, so here we can kind of give our shape, our curve, about what's going on. Okay, so here's our growth. It's still growth because our number that is attached to our exponent is greater than 1, so it's still growth. Okay, and again, if we look at domain and range, domain, still all real numbers. We're hitting everything, the negatives and the positives. But the range this time doesn't involve 0 because now we're crossing the x-axis. Okay, so one really easy way to figure it out if the asymptote is not 0 is just by looking in your table. If you keep going up to the negative direction, it's getting really, really close to 3, or negative 3, excuse me, negative 3. And it's never going to touch it though, but it's getting really, really close to it. So we're going to need all the y's greater than, because we're hitting more positive stuff, negative 3. Okay, so the range, or all the y's, is just everything greater than negative 3, but it's not going to equal negative 3 because it's not going to cross at negative 3 on the graph. Okay, so exponential growth models are used a lot in the real world. So when a real life quantity increases by a fixed % each year, the amount y of the quantity after t years can be modeled by this equation. So y equals a, and in parentheses 1 plus r to the tth power. And in this case, a is the initial amount, t is time, r is the % increase written as a decimal, and 1 plus r is the growth factor. So a lot of times this can be used in real life situations like population growth, money that appreciates, bacteria growing, just a lot of real world applications to exponential growth models or equations. So like in example 5, we'd have that in 1996 there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by about 92% each year. First, we're going to write an exponential growth model. So our formula for exponential growth looked like this. Okay. And A represented our initial amount. So the initial amount of computer viruses and computer security incidents was 2,573. Then we had that parenthesis 1, and then plus r, but this is special, and I forgot to mention it on the previous slide. Okay, we're going to put all percentages or all the rates into a decimal. Okay, so if I take 92% and put a decimal point on the end because we didn't have one in it, I'm going to move it 2 places to the left, and I'll have my decimal. So 0.92 is what I need. And T just means time in years. So my T is just going to be 7 because that's the 7 years we need. Okay. And how many incidents were there in 2003? So the difference in years from 2003 and 1996 is that 7 years. So that's why we put 7 in for T. So if we calculate that from our growth model, we could straight up put that in the calculator and it would be approximate. So if we clear out what we have from the table stuff, we have 2,573, parenthesis 1 plus our percentage rate as a decimal raised to 7 years. And we are dealing with computer viruses and other security incidents. So if we round this up, we have 247,485 computer viruses. So 247,485 computer viruses. So make sure you label it what's going on, because just that number doesn't tell what application we're using it for. Okay, money, bacteria, population, computer viruses. Okay. And the last one we're going to talk about today is the compound interest. It's also a part of the exponential growth model, okay? But compound interest strictly uses money, okay? So compound interest is just the interest paid on the initial investment called the principal, okay? And on previously earned interest. So P is your principal, R is the annual rate, and we're writing it as a decimal still. N is the number of times compounded per year. Okay, so if compounded is in the word problem, then you're going to use compound interest formula. And A is the amount in the account after you calculate using the formula, and T is still in years. So our last example here, we're going to deposit $4,000 in an account that pays 2.92% annual interest. Find the balance after 1 year if the interest is compounded with the given frequencies, quarterly and daily. So let's first talk about quarterly, but let's remind ourselves of that compound interest formula. Okay, so I'm starting out with my principal, or the money I initially had, which was $4,000. And I got 1 plus, and my R is my interest rate. But remember, we need it as a decimal. But even though it has a decimal point right now, I still have to move it 2 places. Okay. So 2.92% is really 0.0292 as a decimal. So that goes up top in the fraction. And then N is the number of times it was compounded. Okay, so quarterly, with respect to a year, just happens 4 times a year. Think of 4 quarters makes $1. Okay, so 4 times a year, or every 3 months, this gets compounded. So 4 times a year. And again, N was the 4 times a year times T. Okay, and it says after 1 year. So T is just going to be 1. Okay, and again, this is going to be approximate. So if we put this on the calculator now, start out with $4,000, and we're adding 1 plus our fraction, let me get that decimal point out of there, 0.0292. all over 4, parentheses, and raise it to 4 again for 4 times a year times 1 year. Okay, so we're dealing with money, so we're going to round it to the nearest hundredth because we need some cents. So that 5 makes the 8 go to a 9. So 4,118 and 9 cents. So make sure you label it with money because, again, we don't know what we're talking about unless we label what we're given. Okay, so here we are quarterly. And daily, though, so it's the same formula, but your end's going to change because all the other info didn't change at all. Okay, so the end's going to change. Well, quarterly meant 4. Daily, think about how many times in a year. Well, that's 365 times a year. So 365 is your n, and in the exponent, and it's still for 1 year. So again, we're going to put this in there. So $4,000, and then 1 plus the fraction 0.0292 for the rate, all over 365 days. Close it up and raise it for 1 year. So again, we're going to raise it to the nearest cents, so 52 cents on this one. Okay, and make sure to label it dollars because what we're working with is money. Okay, so the difference between quarterly and daily is just by a mere few cents. Okay, so when you compare and see what's the better deal to have, compounded quarterly or daily, you can calculate to see what's the better option. Okay, so the compound interest is used a lot with money, but growth overall can help you determine how much interest you can accrue in a bank and like a savings account, okay, over a specified given amount of time, okay, and it also can help out with population growth, both like the census and bacteria growth and a whole lot of other kind of cell repopulating exponentially.